The morning of July 9, 1944, Saipan's Aslito airfield. Amid the wreckage of hastened Japanese evacuation, American Marines discovered something that would prove more valuable than capturing 100 enemy aircraft intact. Scattered across a makeshift maintenance area, partially disassembled and surrounded by technical documentation, sat the radio equipment from a downed F6F Hellcat. Japanese engineers had been in the middle of a desperate examination when the American advance forced them to flee. The radio sets remained, their cases opened, components exposed, circuit diagrams spread across workbenches now abandoned under artillery fire. This wasn't simple salvage work. The Japanese had been conducting systematic technical analysis, photographing every component, measuring every specification, trying to understand how American pilots were coordinating attacks with a precision that seemed almost supernatural. Within hours, American technical intelligence officers were reading those Japanese notes, and what they discovered revealed just how completely the communications gap had contributed to Japan's disintegrating air campaign across the Pacific. For nearly 3 years, Japanese naval aviators had been reporting something that seemed impossible to their commanders. American fighters didn't just stumble onto targets. They appeared with uncanny timing, positioned perfectly, attacking in coordinated waves that suggested some form of communication far beyond what Japanese doctrine considered practical. Fighter pilots described enemy formations that seemed to know exactly where Japanese aircraft were, even at distances exceeding 30 miles. They reported American fighters vectoring onto targets with precision that implied real-time coordination between carriers, combat air patrol, and strike groups. Most disturbing, they described American pilots talking to each other during combat, calling out threats, coordinating attacks, directing each other through the chaos of aerial battle, as if they were standing in the same room rather than separated by miles of open sky at 300 miles per hour. Japanese intelligence officers had initially dismissed many of these reports as combat stress or exaggeration. Radio communication in fighters was possible, certainly. Japanese aircraft carried radios, but reliable voice communication beyond 10 or 15 miles was considered impossible, given the limitations of vacuum tube technology, the power requirements, and the weight constraints of fighter aircraft. The idea that Americans had solved these problems seemed to violate basic physics. Yet, the combat results demanded explanation. American fighters appeared where they shouldn't have been, responded to threats with impossible coordination, and directed complex attacks with a precision that suggested omniscient battlefield awareness. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Hellcat radio discovery on Saipan provided the first hard evidence that Japanese assumptions about communications technology had been catastrophically wrong. The equipment the Marines recovered wasn't experimental or specialized. This was standard production equipment installed in every Hellcat rolling off Grumman's assembly lines. The primary radio was a General Electric identification friend or foe transponder, integrated with voice communication capabilities. The secondary set was an AN, ARC-5 command radio, a compact yet sophisticated system that combined transmitter, receiver, and intercom functions in a package small enough to fit behind the pilot's seat. American intelligence officers examining the Japanese documentation found detailed measurements, circuit diagrams traced onto rice paper, and calculations attempting to understand how the systems achieved their performance specifications. The Japanese engineers had been thorough, professional, and increasingly desperate in their analysis, because what they were discovering contradicted everything they understood about radio technology limitations. The AN, ARC-5, could maintain reliable voice communication at ranges exceeding 100 miles under normal conditions, triple that figure with proper atmospheric conditions and elevation advantages. It operated across multiple frequency bands, allowing pilots to switch channels to avoid interference or jamming. The receiver sensitivity was remarkable, pulling clear signals from weak transmissions that Japanese equipment would render as incomprehensible static. Most impressive was the transmitter power output, sustained reliably without the overheating problems that plagued Japanese military radios when pushed to maximum output. The system weighed approximately 28 pounds, complete with installation hardware. Japanese engineers calculated that an equivalent system built with their available components and manufacturing techniques would weigh at least 60 pounds and still wouldn't achieve half the AN Arc 5's range or reliability. The capture wasn't the first time Japanese forces had encountered American radio equipment. Throughout the Pacific Campaign, damaged American aircraft had been recovered, some with communications gear intact enough for examination. But previous captures had been fragmentary, damaged by combat or fire, incomplete enough that Japanese engineers couldn't fully understand the integrated system design. The Saipan discovery was different. Here were complete radio sets with installation manuals, maintenance documentation, even some spare components the Japanese maintenance crews had salvaged from other wrecks. For the first time, Japanese engineers could see the entire communications architecture that gave American pilots their seemingly impossible coordination capabilities. The equipment was immediately transported to Japan, arriving at the Yokosuka Naval Air Technical Arsenal by late July 1944. The same facility where captured Hellcat airframes had been analyzed now turned its attention to the radio systems those airframes carried. Senior communications engineers gathered, understanding that what they were about to examine might explain Japanese naval aviation's accelerating collapse across the Pacific. The war had reached a point where understanding enemy capabilities mattered less than it once had, because Japan lacked the industrial capacity to respond effectively. But professional curiosity and desperate hope drove the analysis forward. Perhaps understanding American communications advantages would reveal a weakness, some vulnerability that could be exploited, or at minimum, some technical insight that could improve Japanese systems enough to slow the hemorrhaging of pilots and aircraft. The initial examination began with the most basic question. How were the Americans generating sufficient transmitter power to achieve such extraordinary range without cooking the vacuum tubes or draining aircraft batteries? Japanese military radios typically operated at transmitter power outputs between 3 and 6 watts, carefully limited to prevent tube failures that would render entire aircraft incommunicado during critical missions. Higher power outputs were theoretically possible, but Japanese vacuum tube manufacturing couldn't produce tubes reliable enough to handle sustained operation at increased power levels. The tubes would overheat, their filaments would fail, or the envelope glass would crack from thermal stress. 3 to 6 watts of transmitter power gave Japanese pilots radio communication ranges of approximately 10 to 15 miles under ideal conditions, often less in actual combat with interference and aircraft electrical system noise-degrading signal quality. The AN Arc 5 transmitter operated at sustained power outputs approaching 15 watts, 2 to 3. At times what Japanese systems could manage. The American vacuum tubes simply didn't fail under these operating conditions. Japanese engineers examining the tubes found manufacturing quality that seemed impossible given the quantity of radios American forces were fielding. The tube envelopes showed no signs of thermal stress. The filaments were precisely formed and mounted with supports that prevented vibration damage. The cathode coatings were uniform and stable. Every tube characteristic spoke to manufacturing processes with tolerances Japanese industry couldn't match consistently, especially not in the quantities modern warfare demanded. Chemical analysis of the tube components revealed part of the answer. The Americans were using vacuum tube materials that Japanese manufacturers had stopped being able to source in sufficient quantity by 1943. Tungsten filaments of exceptional purity. Cathode coatings using rare earth elements Japan could no longer import. Envelope. Glass with specific thermal expansion properties requiring raw materials Japanese factories couldn't obtain. Even when Japanese engineers understood what materials the Americans were using, acquiring those materials in wartime was impossible. The shipping lanes that had once brought strategic materials to Japan were now graveyards patrolled by American submarines. Domestic production of advanced materials had never been adequate for total war consumption rates, and Allied bombing was systematically destroying what limited production capacity existed. The transmitter circuit design revealed another advantage. American engineers had developed sophisticated frequency modulation techniques that improved signal clarity and reduced power requirements for equivalent range. Japanese military radios used primarily amplitude modulation, simpler to implement but less efficient and more susceptible to interference. The FM circuitry in the AN ARC-V required precision components, stable oscillators, and careful design that Japanese engineers could understand intellectually but couldn't replicate with available manufacturing capabilities. The receiver section was even more impressive. Sensitivity specifications indicated the AN ARC-V could detect and decode signals weaker than what would register as noise floor on Japanese equipment. This extraordinary sensitivity came from multiple design advantages working in concert. The input stages used tubes selected for low noise characteristics, something that required extensive testing and quality control during manufacturing. The intermediate frequency stages employed carefully designed transformers wound to tolerances measured in fractions of a millimeter. The audio output stages recovered signals from weak inputs that Japanese receivers would simply ignore as background static. Most significantly, the Americans had solved the selectivity problem that plagued Japanese receivers. Military radios needed to operate across crowded frequency bands where multiple transmitters might be broadcasting simultaneously. Japanese receivers would often pick up multiple signals at once, creating garbled audio that made communication impossible during high-tempo operations. The AN ARC-V employed sophisticated filtering that allowed pilots to hear their assigned frequency clearly, even when nearby frequencies carried other traffic. This selectivity required precision tuning components, stable capacitors, and careful shielding, all manufactured to standards that Japanese production facilities struggled to achieve. The power supply revealed yet another gap. Aircraft electrical systems were hostile environments for sensitive electronics, with voltage fluctuations, radio frequency interference from ignition systems, and mechanical vibration that could shake components loose or damage delicate connections. Japanese radio designers spent enormous effort trying to filter and stabilize power supplies, accepting weight, penalties, and complexity to protect fragile vacuum tube circuits. The AN ARC-V power supply was remarkably compact and robust, handling aircraft electrical system variations without the heavy filtering equipment Japanese designs required. American engineers had apparently developed voltage regulation circuits that were both more effective and lighter than anything Japanese designers had achieved. The dynamotor that converted aircraft battery voltage to the high voltages vacuum tubes required was particularly impressive, efficiently delivering clean power across a wide input voltage range. Japanese engineers testing captured American aircraft batteries discovered another advantage contributing to communications performance. The batteries themselves were superior, delivering more stable voltage under high current draw conditions. American metallurgy and chemical engineering had created battery designs with better energy density, longer service life, and more reliable performance than Japanese batteries could provide. This seemingly minor detail had cascading effects. Better batteries meant radio equipment could draw more power without voltage sagging. More stable power meant tube circuits operated within optimal parameters consistently. Optimal circuit operation meant maximum range and reliability. Every component in the American communications system revealed similar patterns. Superior materials enabled better performance. Better performance allowed more aggressive design parameters. More aggressive designs delivered capabilities Japanese systems simply couldn't match. The installation documentation proved almost as revealing as the hardware itself. American technical manuals described maintenance procedures that assumed aircraft would be serviced by mechanics with moderate training, not specialized communications technicians. Troubleshooting guides identified common problems and provided clear diagnostic steps. Replacement procedures were straightforward, with components designed for quick swapping under field conditions. Japanese radio equipment, by contrast, required careful adjustment by trained technicians. Tubes needed individual bias adjustments when replaced. Alignment procedures demanded test equipment that wasn't always available at forward airfields. Repairs often meant sending the entire radio back to depot-level facilities because field maintenance lacked the knowledge or tools to fix complex problems. This maintainability difference had profound operational implications. American squadrons could keep radios functioning with basic tools and spare parts, maintaining high equipment readiness rates even during sustained combat operations. Japanese squadrons watched readiness rates decline as radios failed and couldn't be repaired quickly. By mid-1944, it wasn't unusual for Japanese fighter formations to have 30% or more of their aircraft flying with degraded or non-functional radios, pilots reduced to hand, signals and pre-briefed tactics because they couldn't communicate in flight. The Americans maintained radio readiness rates above 85% throughout the Pacific Campaign, ensuring that communications advantages remained consistent rather than degrading over time. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The tactical implications of the radio capability gap became brutally clear when Japanese intelligence officers compiled combat reports alongside the technical analysis. Throughout 1944, American fighter direction officers aboard carriers had been controlling aerial battles with a precision that Japanese commanders found incomprehensible. Now, the captured radio equipment explained exactly how American forces achieved their seemingly omniscient battlefield awareness. The system worked with elegant simplicity, made possible by reliable long-range communications. Radar operators aboard American carriers would detect incoming Japanese formations at ranges exceeding 100 miles. Fighter direction officers would vector combat air patrol fighters toward the threat, providing continuous updates on enemy bearing, altitude, and numbers. The Hellcat pilots would receive these updates clearly, even at maximum interception ranges, allowing them to position themselves advantageously before visual contact. As combat developed, pilots could communicate with each other, calling out threats, coordinating attacks, requesting assistance, all in real time across distances that would render Japanese radios useless. Japanese fighter formations operated under entirely different constraints. Radio communication was possible only when aircraft remained within visual range of each other, roughly 5 to 10 miles depending on atmospheric conditions. Beyond that distance, pilots were alone, unable to receive updates from their carriers, unable to coordinate with wingmen who had become separated, unable to call for help if they encountered overwhelming opposition. Japanese tactical doctrine had evolved around these limitations, emphasizing tight formations that kept aircraft within radio range and pre-briefed attack plans that didn't require real-time communication. But these tactics meant Japanese formations were rigid, unable to adapt quickly to changing conditions, vulnerable to American fighters that could coordinate attacks from multiple directions simultaneously. Combat reports from the Battle of the Philippine Sea in June 1944 illustrated the consequences with devastating clarity. Japanese strike aircraft approaching the American fleet had been intercepted by Hellcats vectored to perfect positions by carrier-based fighter directors. The American fighters had concentrated their attacks on Japanese bombers first, coordinating through radio communication to ensure multiple fighters didn't waste ammunition on already destroyed targets. Japanese fighter escorts, unable to coordinate effectively beyond visual range, found themselves drawn into individual dogfights, while bombers they were supposed to protect were systematically destroyed. American pilots reported the engagements almost casually, describing how fighter direction officers had guided them to targets, how they had coordinated their attacks through radio calls, how they had disengaged when low on ammunition while fresh fighters arrived to continue the battle. The Japanese formations had been slaughtered, losing 300 aircraft in a single day, many shot down by pilots they never saw because American coordination allowed attacks from unexpected angles. The psychological impact on Japanese pilots was profound and demoralizing. They weren't just fighting enemy aircraft. They were fighting an entire system that gave American pilots godlike awareness of the battlefield. Japanese pilots described the terror of knowing that somewhere, on a carrier they couldn't see, American controllers were watching them on radar screens, directing fighters to intercept them, coordinating attacks they had no way to counter. The feeling of being hunted by an enemy who always knew where you were, who could see you coming from 100 miles away, who could coordinate responses faster than you could react, destroyed morale more effectively than any amount of combat losses. At least in a fair fight, skill and courage mattered. Against American fighter direction and radio coordination, individual pilot quality seemed almost irrelevant. Japanese naval commanders attempted to develop countermeasures, but every approach ran into the same fundamental problem. They lacked the technology to implement effective solutions. Some officers proposed equipping Japanese fighters with radios powerful enough to match American range capabilities. The captured AN, ARC-5, made it clear this wasn't possible with available materials, manufacturing capacity. Others suggested developing fighter direction capabilities similar to American systems, using ship-based radars to vector Japanese fighters onto targets. Japan had radar technology, certainly, but Japanese radars were less capable than American systems. Japanese radio communications couldn't support the needed coordination at long range, and Japanese carriers lacked the command and control facilities American carriers had been designed with from the beginning. A few desperate proposals suggested extreme measures. Perhaps Japanese pilots could be trained to operate without radio communication entirely, using visual signals and pre-coordinated tactics. This approach ignored the reality that Japanese pilots were already operating with minimal radio coordination and losing catastrophically. Making communications worse wouldn't improve outcomes. Another proposal suggested attempting to jam American radio frequencies, disrupting their coordination advantages. Japanese electronic warfare capabilities were primitive compared to American systems, and any jamming would likely affect Japanese communications more severely than American ones. The Americans had frequency agility, multiple backup channels, and communications discipline that would allow them to work around jamming. Japanese formations would be rendered completely mute. By late 1944, the communications analysis had moved beyond the technical details of the captured radios to confront a more fundamental truth. The AN, ARC-5, wasn't an isolated advantage. It was one component of an integrated system that included radar, fighter direction procedures, carrier command facilities, pilot training, and maintenance infrastructure. Japan could potentially copy the radio design if materials were available, but copying one component wouldn't give them the system. The Americans had built their entire carrier air warfare doctrine around reliable long-range communications. Their tactics assumed pilots could talk to controllers and each other. Their training emphasized radio discipline and communication procedures. Their carriers were designed with dedicated combat information centers, where fighter direction officers could coordinate defensive responses. Capturing and understanding American radio equipment revealed what Japan was facing, but revealed no practical path to matching those capabilities. The materials analysis conducted alongside the radio examination exposed the deeper crisis facing Japanese military production. Engineers cataloging the components in the AN ARC-5 identified dozens of materials Japan could no longer obtain in sufficient quantities. The copper wire in the transformers required high-purity copper with specific electrical properties. Japanese copper supplies had been adequate in peacetime but couldn't meet wartime consumption rates, especially after Allied submarines severed imports from conquered territories. The mica used in capacitors needed to be of exceptional quality to maintain stable electrical properties across temperature ranges and humidity levels aircraft experienced. Japanese mica deposits were limited, and what could be mined often wasn't suitable for precision electronic components. The rubber insulation on wiring required synthetic compounds Japan's chemical industry couldn't produce consistently. Natural rubber had become almost unobtainable, and substitute materials degraded quickly, causing electrical failures that rendered radio equipment unreliable. Even common materials like aluminum showed quality differences that accumulated into significant performance gaps. The aluminum chassis and component housings in the AN Arc 5 used alloys with better strength-to-weight ratios and improved corrosion resistance compared to Japanese aluminum. American metallurgy had produced materials that were incrementally better across dozens of applications, and these small advantages compounded. Better aluminum meant lighter, stronger equipment. Better copper meant more efficient transformers. Better insulation meant more reliable operation. Every material advantage enabled design choices that improved performance, and Japan had fallen behind in nearly every category. The inspection of manufacturing techniques revealed equally disturbing gaps. American radio components showed evidence of mass production processes that maintained remarkable quality consistency. Resistors had uniform tolerances. Capacitors showed identical electrical characteristics across production batches. Vacuum tubes met specifications reliably. Japanese production of equivalent components suffered from far greater variability, with individual components often requiring hand selection and matching to achieve acceptable performance. This variability meant Japanese radios needed extensive adjustment during installation and required frequent realignment to maintain performance. American radios worked correctly when installed and stayed working with minimal intervention. The standardization of American components particularly impressed Japanese engineers. The tubes, resistors, capacitors, and other parts in the AN Arc 5 were common standard components used across multiple radio models and equipment types. This standardization simplified logistics enormously. Spare parts for one radio type could often substitute in other equipment. Mechanics, familiar with one system, could service others. Production could be scaled efficiently because the same components were manufactured in huge quantities for multiple applications. Japanese radio equipment used custom components specific to each model, complicating logistics, limiting production efficiency, and ensuring that spare parts for one radio type were useless for others. By October 1944, the technical reports from Yokosuka were circulating through Japanese Naval Command, accompanied by increasingly pessimistic assessments of Japan's ability to close the capability gaps the captured equipment had revealed. Captain Takeo Shibata, who oversaw much of the communications analysis, wrote in his summary report that American radio superiority wasn't a matter of isolated technical advantages, but represented the culmination of superior industrial infrastructure, better materials science, more advanced manufacturing processes, and design philosophies that prioritized reliability and maintainability over minimum weight and maximum theoretical performance. His report concluded that Japan lacked the industrial capacity to match American communications capabilities, and that this disadvantage would continue contributing to unsustainable aircraft losses for the duration of the conflict. The strategic implications extended beyond tactical aviation. If American forces enjoyed such overwhelming advantages in something as basic as radio communications, what other capability gaps existed that Japan hadn't yet discovered? Intelligence. Officers began reviewing every aspect of American military equipment with fresh skepticism toward Japanese assumptions about technological parity. They found evidence of similar gaps everywhere. American radar was more capable than Japanese intelligence had estimated. American torpedoes worked far more reliably than Japanese equivalents. American damage control equipment and procedures were superior. American logistics and supply systems delivered spare parts and ammunition with an efficiency Japanese forces couldn't approach. The captured Hellcat radio had opened a window onto a broader truth. America wasn't just outproducing Japan. America was out-engineering Japan across virtually every technical domain that mattered for modern warfare. Japanese attempts to apply lessons from the captured radios proceeded despite the grim assessments of what could be realistically achieved. Mitsubishi and Japan Radio Company received contracts to develop improved aircraft radios incorporating insights from the AN Arc 5 analysis. Engineers worked with available materials and manufacturing capabilities to create systems that would at least narrow the performance gap, even if matching American capabilities remained impossible. The result was the Type 3 air-to-air radio, which entered limited production in early 1945. The Type 3 achieved transmitter power outputs of approximately 8 watts, a significant improvement over earlier Japanese radios, but still barely half what the AN Arc 5 delivered. Range increased to perhaps 25 miles under good conditions, better than before, but still leaving Japanese pilots isolated compared to American formations that could coordinate across 100 miles. The receiver was more sensitive than previous Japanese designs, but couldn't match American performance. Most frustratingly, the Type 3 required materials in such short supply that production rates never exceeded a few dozen units per month. Most Japanese fighters continued flying with older radios or no radio equipment at all, as shortages worsened through 1945. The maintainability problems that plagued Japanese radio equipment grew worse as the war situation deteriorated. Skilled technicians were increasingly scarce, drafted into combat units or killed in bombing raids. Replacement components became unavailable as production facilities were destroyed. By the final months of the war, Japanese fighter squadrons were cannibalizing radios from damaged aircraft to keep a handful of sets functioning in operational aircraft. Even then, radio discipline had largely collapsed. Pilots who had functioning radios often couldn't communicate effectively because their wingmen's radios had failed, or because frequencies were so crowded with distress calls and desperate communications that coordinated operations became impossible. The Americans, meanwhile, maintained their communication advantages right through the final days of the war, continuing to coordinate strikes with precision that Japanese forces could only watch helplessly as it developed. French aviation engineers who evaluated captured Japanese aircraft after the war conducted comparative analyses that quantified the radio performance gap with brutal precision. A 1948 report examining the Mitsubishi, a 6M0, noted that the Type 3 air-to-air radio, Japan's best wartime fighter communications equipment, achieved reliable voice communication at ranges of approximately 15 to 20 miles. The report compared this to contemporary American equipment and noted that the AN Arc 5 installed in Hellcats had been replaced by even more capable systems by war's end, some achieving reliable communication at ranges exceeding 150 miles. The performance gap hadn't closed, it had widened. Japanese radio technology had improved incrementally, while American systems had leaped forward with each generation of equipment. The laver, Soviet Union, which received substantial quantities of American equipment through Lend-Lease during the war, conducted their own evaluations comparing American and Japanese communications technology. Soviet reports from 1946 noted that American aircraft radios were dramatically superior to both Japanese and early Soviet equipment. The Americans had solved technical problems that Soviet engineers were still struggling with, achieving performance specifications that seemed impossible given the weight and power constraints of fighter aircraft. These Soviet assessments led directly to post-war programs that attempted to copy American radio designs, with varying success depending on whether Soviet industry could access the necessary materials and manufacturing equipment. The broader lesson about communications in modern warfare became a foundational principle for post-war military doctrine across all major powers. The captured Hellcat radio had demonstrated that reliable, long-range communication wasn't a luxury, but a fundamental requirement for effective air operations. American forces had proven that fighters equipped with capable radios and directed by carrier-based controllers could achieve air superiority against numerically equal or even superior forces, lacking equivalent communications. This principle extended beyond aviation into ground warfare, naval operations, and eventually into the joint operations doctrine that defined late 20th century military thinking. Communications infrastructure became recognized as a combat multiplier as important as firepower or protection. When the United States Air Force and Navy developed requirements for post-war fighters, radio capability received unprecedented emphasis. The specifications for aircraft, like the F-80 Shooting Star, F-9F Panther, and F-86 Sabre, included detailed communications requirements that would have seemed impossibly demanding just a few years earlier. Multi-channel radios, with frequency agility, long-range communication capability, integration with ground control intercept systems, all became standard features rather than specialized equipment. The lessons learned from Japanese radio deficiencies informed American thinking about ensuring communications advantages remained permanent rather than temporary. Japanese post-war aviation development took communications seriously in ways wartime programs never had. When Japan eventually rebuilt its aviation industry in the 1950s and began producing fighters for the newly formed Japan Self-Defense Forces, radio equipment specifications matched contemporary international standards. Japanese engineers who had examined the captured Hellcat radio in 1944 influenced post-war designs, ensuring that the next generation of Japanese military aircraft wouldn't repeat the catastrophic communications disadvantages that had contributed to the wartime destruction of Japanese naval aviation. The institutional memory of fighting blind while enemies coordinated perfectly shaped Japanese military thinking for decades. The story of the captured Hellcat radio intersects with a broader narrative about how wars are won through the accumulation of small advantages in dozens of technical domains. No single capability gap defeated Japanese naval aviation. It was the cumulative weight of disadvantages across radios, radar, pilot training, industrial production, logistics, material science, and engineering philosophy that created a situation where Japanese forces couldn't compete regardless of individual courage or tactical skill. The radio was simply one component of this larger pattern, but it was a revealing component because communications advantages touched every aspect of air operations. Better radios enabled better tactics. Better tactics allowed more aggressive operations. More aggressive operations led to higher enemy losses and lower friendly casualties. Lower casualties meant experienced pilots survived to pass knowledge to new pilots. Every advantage compounded and reinforced every other advantage until the gap between American and Japanese capabilities became unbridgeable. The engineers who examined the captured equipment at Yokosuka understood this. Their reports documented technical specifications with professional precision, while increasingly acknowledging the strategic hopelessness of Japan's situation. They were looking at equipment that represented an industrial and technological system Japan couldn't match, even if the war lasted years longer. The materials weren't available. The manufacturing capabilities didn't exist. The engineering knowledge could be learned, but couldn't be applied without resources that had become inaccessible. Understanding the problem completely didn't provide solutions. It simply illuminated exactly why Japan was losing and would continue losing regardless of how many battles remained to be fought. There's a particular tragedy in the thorough professionalism of the Japanese analysis. The engineers didn't make excuses. They didn't claim Japanese equipment was adequate when clearly it wasn't. They documented American technical superiority honestly and recommended changes to Japanese practices that might narrow some of the gaps. But by late 1944, honest assessments and good recommendations couldn't change outcomes. The war had entered its final phase where Japan's defeat was mathematically certain, and technical intelligence about enemy capabilities served mainly to explain how complete that defeat would be. The captured Hellcat radio helped Japanese engineers understand they were fighting an enemy whose advantage in one seemingly minor area, aircraft communications equipment, contributed to an air campaign that was systematically destroying Japanese naval aviation. Understanding that didn't make it possible to stop it. By the summer of 1945, the radio equipment that had been so carefully examined at Yokosuka sat in storage, just another piece of captured equipment in a facility that would soon be occupied by American forces. The engineers who had studied it had moved on to more immediate concerns, analyzing incendiary bomb damage, attempting to develop civil defense measures against firebombing, preparing for the invasion everyone knew was coming. The technical reports they had written gathered dust, valuable intelligence that arrived too late to matter strategically. American forces occupying Yokosuka after Japan's surrender found the Hellcat radio, among other captured American equipment, all tagged with Japanese documentation showing the thoroughness of enemy analysis. It was a strange artifact, American technology examined by Japanese engineers who had understood its superiority completely while lacking any ability to duplicate it. The legacy of that captured radio extends into how we think about technological competition in warfare. It demonstrated that superior equipment matters enormously, but only when backed by the industrial infrastructure to produce it in quantity, the logistics to maintain it in the field, and the doctrine to employ it effectively. Japan captured American radio equipment, analyzed it expertly, understood its advantages completely, and gained nothing from that knowledge because understanding alone couldn't overcome fundamental resource and industrial limitations. The Americans built their air warfare doctrine around reliable long-range communications because they could manufacture capable radios by the thousands, because they could train pilots to use them effectively, because they could maintain them in combat conditions, and because they had the carriers and command facilities to employ them as part of an integrated system. Japan lacked every component of that system except the understanding that it existed and was devastatingly effective. When military historians examine the Pacific Air War, the communications gap revealed by captured Hellcat radios serves as a perfect example of how modern warfare is won through integrated systems rather than individual weapons. The radio itself was just one component, but it enabled tactical advantages that multiplied across every engagement. Fighter direction, coordinated attacks, mutual support, all the tactics that gave American pilots overwhelming advantages depended absolutely on reliable long-range communication. Without those radios, Hellcats would still have been formidable aircraft, but they wouldn't have achieved kill ratios approaching 19-1. Without reliable communications, American carrier groups would have been far more vulnerable to Japanese strikes. The radio was simultaneously a minor component and a critical enabler of American air superiority, important precisely because it connected everything else into a functioning system. The captured equipment sits in museums now, preserved examples of World War II technology. The Japanese technical reports remain in archives, hundreds of pages of careful analysis that documented one nation's attempt to understand another's technical advantages. They tell a story about the Pacific War that goes beyond battles and casualties to examine the industrial and technological foundations of modern military power. Japan fought courageously and skillfully, but couldn't overcome disadvantages that compounded across dozens of technical domains. The Hellcat radio was one of those domains, and examining it revealed to Japanese engineers exactly how completely American industrial might had manifested in superior equipment across virtually every category that mattered. That knowledge was precise, professional, and ultimately useless because wars aren't won by understanding enemy advantages. They're won by possessing advantages that enemies can't overcome, and by 1944, America possessed those advantages in abundance, while Japan possessed only the capacity to document how outmatched they had become. The most haunting aspect of the captured Hellcat radio analysis wasn't what Japanese engineers discovered about American technology. It was what they discovered about themselves. Every measurement, every circuit diagram, every materials analysis forced them to confront how far Japanese industry had fallen behind, not just in one area, but systematically across every technical domain modern warfare demanded. The radio became a mirror reflecting Japan's industrial inadequacy, and that reflection couldn't be ignored or rationalized away with claims of superior fighting spirit or tactical innovation. In the decades following the war, former Japanese naval engineers, who had participated in the Yokosuka analysis, wrote memoirs and technical histories that revealed the psychological weight of that work. They described the growing sense of hopelessness as each component examined revealed another insurmountable gap. They recalled the bitter irony of understanding exactly why Japan was losing while possessing no means to apply that understanding effectively. Some wrote about the relief they felt when the war finally ended, not from escaping danger, but from escaping the futile exercise of documenting defeat in technical specifications and performance measurements. The captured radio also influenced how post-war Japan approached technological development. The experience of fighting with systematically inferior equipment while facing enemies with overwhelming material advantages shaped Japanese industrial policy for generations. When Japan rebuilt its electronics industry in the 1950s and 60s, the emphasis on quality control, manufacturing precision, and materials science reflected lessons learned during the war. Japanese engineers who had examined American equipment and found it superior in every measurable way were determined that future Japanese products would never again suffer from such comprehensive technical inferiority. By the 1970s, Japan had become a global leader in electronics manufacturing, producing radios, televisions, and communication equipment that competed successfully with American and European products. Some historians have drawn direct lines between the wartime technical intelligence work at facilities like Yokosuka and Japan's post-war economic miracle. The engineers who documented American technical superiority in 1944 became the industrial leaders who ensured Japanese manufacturing achieved world-class quality standards by the 1960s and 70s. The captured Hellcat radio, in this interpretation, taught lessons that ultimately proved more valuable in peace than they ever could have been in war. The equipment itself has largely disappeared. Unlike aircraft that could be preserved in museums, radio equipment from World War II was generally scrapped or lost to time. The Japanese technical reports survive in archives, testimony to thorough professional work conducted under desperate circumstances. They remain valuable to historians not for their technical content, which is now obsolete, but for what they reveal about how nations confront technological inferiority during existential conflicts. Japan looked directly at its disadvantages, documented them with precision, and found no solutions because some problems can't be solved through better understanding alone. Sometimes, knowing exactly why you're losing is simply the clearest possible view of inevitable defeat, and the captured Hellcat radio provided that clarity with unforgiving technical precision to engineers who deserved better equipment to analyze and a better war to fight. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.